This video is going to talk about what is cumulative distribution function, which we usually call a CDF, and examples will be given later. So let's start. What is CDF? By definition, we know CDF describes the probability that a real-valued random variable, capital X, with a given probability distribution will be found to have a value less than or equal to small x. We use capital Fx to represent the cumulative distribution function, which is Fx equal to the probability of capital X, the random variable, less than or equal to small x, a given value. CDF is also the total area under the graph of PDF, which is the probability density function. There are totally of two types of CDF. They are the CDF for discrete random variable and for the continuous random variable. Then move on to talk about the properties of the CDF. There are a total of 6 properties of the CDF. Third, CDF is a non-decreasing function and right continuous, just like the graph on the right. Second, CDF is bounded between 0 and 1 for all x. That is, for x tends to negative infinity, fx will tend to 0, and for x tends to positive infinity, fx will tend to 1. Third, from property 1, since it must be non-decreasing and right continuous, so if we know x1 less than or equal to x2, then we also know fx1 is less than or equal to fx2. Fourth, for the probability of capital X is between x1 and x2, two given values, is equal to capital F x2 minus f x1. Fifth, the first derivative of CDF will get back to the PDF. Also note that the probability of capital X larger than small x is equal to 1 minus fx. After we talk about the properties and the definition of CDF, and before we move on to talk about the CDF for discrete and continuous random variables, let us talk briefly what is the difference between discrete and continuous. So, for discrete random variables, it refers to the countable number of distinct values, such as 0, 1, 2, 3, 4, etc., and which are usually counts. For discrete random variables, the examples are like the binomial distribution and the Poisson distribution. For the continuous random variables, it refers to the data that can take infinitely many values. The examples are like the normal distribution and exponential distribution. Okay, then we'll move on to talk about the first case, which is the CDF for discrete random variable. We first let R's to be a set, and we use the blanket to represent the set. And in this set, we have x1 to xn n values, and we know the PDF fx for each values, which is fx1, fx2, etc. Then, by definition, we can know the capital Fx, which is the cumulative distribution, is equal to the probability of capital X, the random variable, less than or equal to small x, the given values. And this will be equal to the summation or probability of xi for x smaller than or equal to xi. Xi will be taken from x1 to xn in values. Then let's take a look at the example. We are given the distribution of capital Fx such that if x smaller than or equal to 1, the probability will be equal to 0.2. If x larger than 1 but smaller than 2, the probability will be equal to 0.5. If x larger than 2 but smaller than or equal to 4, the probability will be equal to 0.1. And if x larger than or equal to 6, the probability will be equal to 0.2. by the distribution function we are going to find part A f4.5, which is the probability of capital Fx smaller than or equal to 4.5. Part B, probability of capital Fx larger than 4.5. And part C, the probability of capital Fx is between 1.5 and but smaller than or equals to 4.5. For part A, by definition, we have the Fx, which is the CDF, is equal to the summation of all the probability of all value of x. And we can simply use this property. So for part A, f4.5 will be equal to the probability of x smaller than or equal to 4.5, and which is equal to the probability of x equal to 1 plus the probability of x equal to 2 plus the probability of x equal to 4, and we get 0.8. For part B, the property of CDF said that the probability of capital X larger than small x, which is a value, is equal to 1 minus fx. So we have the probability of capital X larger than 4.5 is equal to 1 minus 0.8, which is equal to 0.2. Or we can think of the only case fits in this case, which is the probability of x larger than 4.5 is when x equal to 6. So we also know the probability is equal to 0.2. So part C, we are going to find the probability of x is larger than 1.5 but smaller than or equal to 4.5. By property of CDF, we know the probability of x is between x1 and x2, the two given values, is equal to the difference of two cumulative distribution function, which is fx2 minus fx1. And we are given that f1.5 is equal to 0.2. So the answer for part C, and we are going to get the probability of x is larger than 1.5 but smaller than or equal to 4.5 will be equal f4.5 minus f1.5, which is the difference, is equal to 0.8 minus 0.2 equal to 0.6. We can also think of the probability of capital X larger than 1.5, smaller than 4.5 is equal to f2 plus f4, which is also 0.6. To conclude, for the discrete case, we can write down the CDF fx is equal to when x smaller than 1, fx equal to 0, but if x larger than or equal to 1 but smaller than 2, the CDF will be equal to 0.2. If x larger than or equal to 2 but smaller than 4, the CDF will be equal to 0.7. And if x larger than or equal to 4 but smaller than 6, the CDF equals to 0.8. And finally, if x larger than or equal to 6, the CDF will be equals to 1. After talk about the discrete case, we are going to move on to talk about the continuous case. For a given function of x, fx, we use small f to represent a function, and we can note the CDF will be written as capital Fx is equal to integrate small fx the function from negative infinity to x dx. Note that the limit will be changed according to the different function. For example, we given the exponential function, the negative infinity will change to 0 because due to the limits of the function is changed. We will also take a look at the example for the continuous case. Let's say we have the function is equal to 3 times x squared over 8 for x is between 0 and 2. We are going to find part A, the CDF, Part B, F1, which is the probability of x smaller than or equal to 1. And part C, we given the fx and the CDF in part A. We are going to find the PDF fx back. For part A, from the definition, we know the CDF is equal to integrate fx dx, where fx is the function, so we can substitute the function, which is equal to integrate 3 times x squared over 8 from 0 to x dx. By simple integration skills, integrate x squared dx will get x cubed over 3, and the of 3 will be cancelled with the 3 and the constant, so we can get x cubed over 8, the limit from 0 to x, so we can get the CDF is equal to x cubed over 8. Part B, we can get f1 by replacing x by 1 in the integrals. So we have integrate 3 times x squared over 8 from 0 to 1 dx. Again, we can get 1 over 8 by integrate fx. Part C, we are going to find the PDF. We know the fx, the CDF equals to x cubed over 3 in part A. We are going to have the first derivative of it. So the PDF will be equals to d dx x cubed over 8, which we can get 3 times x squared over 8. Then we can prove that the PDF is equal to the PDF we given in the question. Next, we can now get the CDF of capital Fx is equal to x cubed over 8, and we can prove that by this capital Fx, the CDF, we can get the PDF is equal to 3 times x squared over 8 for x is between 0 and 2, which is plotted as below. So finally, let's do an exercise. In this question, we are given the PDF of set such that the function is equal to 1 times 1 plus set squared over 6 for set is between -2 to 1. In this question, we are going to find part A, the CDF, part B, the probability of set smaller than or equal to 0, and part C for set larger than 0. So here's the answer. For part A, we are going to find the CDF. So f set, the capital F set, the CDF, will be equal to integrate 1 times 1 plus set squared over 6 from -2 to set dz. By simple integration skills, we can get the CDF will be equal to 1 over 6 times set plus set cubed over 3 plus 14 over 3. Part B, we are going to find the probability of set smaller than or equal to 0, which is equal to f0, and we can get it by integrate 1 times 1 plus set squared over 6 from -2 to 0. Again, by simple integration skills, we have the answer, which is equal to 7 over 9. Finally, for part C, we are going to find the probability of set larger than 0. By definition, we know probability of capital set larger than small set, the value, is equal to 1 minus f set, will be equal to 1 minus f0 equal to 2 over 9. Last, we can plot the CDF graph like the one on the right hand side. So that's all for the exercise and this video. That's how simple is CDF. That's all. Thank you for watching this video.